The forest floor is already awake before the sun has fully lifted itself over the canopy. Moist air hangs low, carrying the smell of decaying leaves, fungal spores, and sap. Along the soil's surface, thin, dark lines begin to move with unsettling precision. At first, they look like cracks forming in the ground, fractures spreading through bark and leaf litter. Then the lines sharpen into motion. Thousands of bodies advance in organized streams, each ant maintaining a fixed distance from the one ahead, antennae brushing, legs tapping, chemical signals flowing invisibly between them. This is not wandering. This is deployment. Leafcutter ants emerge from their subterranean city in disciplined columns, spilling from multiple tunnel mouths like conveyor belts of living machinery. Their jaws open and close rhythmically as they march, serrated mandibles honed by evolution not for combat alone, but for industry. These ants are not foragers in the casual sense. They are harvesters feeding an economy that never sleeps. Each individual moves with purpose, guided by pheromone trails laid down moments earlier, updated constantly as conditions change. When a path becomes inefficient or dangerous, chemical signals reroute traffic instantly, redirecting thousands without a single command being spoken. Coordination is not learned here. It is encoded. Above them, the vegetation appears calm, unaware of the approaching extraction. Leaves tremble as scouts arrive first, testing surfaces, tasting plant chemistry, evaluating resistance. Within moments, the cutting begins. Crescent-shaped fragments are carved from living leaves with mechanical precision, each cut optimized to reduce effort while maximizing yield. The ants work in parallel, hundreds cutting at once, their movements synchronized by feedback loops of touch and scent. A leaf does not fall in panic. It is dismantled piece by piece, reduced into transportable units designed to be carried back along the same arterial routes that delivered the workforce. This is where the brutality becomes visible, not as chaos, but as efficiency. No single ant understands the colony's full scale, yet the outcome is total. Green canopies thin. Saplings are stripped bare. In extreme cases, entire trees lose their foliage in a matter of hours. To the untrained eye, this looks like destruction. In reality, it is logistics in its purest form. Leafcutter ants do not eat the leaves they cut. The harvest feeds a subterranean fungus, cultivated deep underground in climate-controlled chambers where temperature, humidity, and airflow are carefully regulated by worker behavior alone. Inside the nest, the colony expands downward and outward, carving vast underground complexes that can extend deeper than a human, is tall and wider than a small building. Millions of individuals may inhabit a single system, each one occupying a narrow functional role. Small workers tend the fungus gardens, removing contaminants and feeding them fresh leaf pulp. Medium workers transport materials and maintain tunnels. Large workers defend the colony, their heads oversized, jaws capable of severing limbs or crushing intruders. This division of labor is not random. It emerges from developmental pathways triggered by nutrition, hormones, and colony demand. The colony adjusts its workforce composition dynamically, responding to threats, seasonal changes, and food availability with industrial precision. Warfare, in this system, is not emotional or reactive. It is mathematical. When leafcutter colonies clash, they do not charge blindly. They assess density, trail strength, and resource value. If a neighboring colony encroaches on foraging territory, chemical alarms ripple through the workforce. Soldiers mobilize first, positioning themselves at tunnel entrances and trail junctions. Workers continue harvesting even as combat begins, because the colony cannot afford to halt production. Losses are calculated into the system. Individual ants are expendable. The fungus must survive. Battles unfold as grinding contests of attrition. Ants lock jaws, tear legs free, and pile bodies into barricades that physically reshape the battlefield. Chemical weapons are deployed, formic acid sprayed at close range, overwhelming sensory systems and soft tissue. Yet even here, efficiency rules. Wounded ants are often carried back to the nest, not out of compassion, but because their bodies can be recycled, their nutrients reclaimed. The colony wastes nothing. Every loss is metabolized into future labor. This industrial mindset extends into how leafcutter ants reshape ecosystems. Their relentless harvesting alters plant growth patterns, favoring species that regenerate quickly or produce chemical deterrents. In response, some plants evolve tougher leaves, toxic compounds, or symbiotic relationships with other insects that defend them. The ants adapt in turn, refining their selection, avoiding certain species, exploiting others. This is not dominance in isolation. It is an evolutionary arms race played out across generations, driven by the colony's constant need for fuel. Inside the nest, the fungus itself evolves alongside the ants. It cannot survive without them, and they cannot survive without it. The fungus breaks down plant material that ants cannot digest, converting cellulose into nutrients the colony can absorb. In return, the ants protect the fungus from parasites, mold, and invasive microbes. Specialized workers patrol the gardens, detecting contamination through smell alone. When a foreign fungus appears, it is removed immediately, sometimes with the infected worker sacrificing itself to prevent spread. This is agriculture without sentiment, refined over millions of years. What makes leafcutter ants truly unsettling is not their violence, but their scale. No single ant is intelligent in the human sense, yet collectively they solve problems of traffic flow, supply chain optimization, climate control, and defense that rival human infrastructure. Their success comes from strict adherence to rules, relentless repetition, and an absolute prioritization of the collective. Work becomes power not through ambition, but through inevitability. The colony grows because it must. Expansion is not a goal, it is a consequence. As the sun climbs higher, the marching lines thicken. Leaves continue to fall in precise arcs, carried away by tireless workers who never pause, never question, never deviate. Somewhere beneath the forest floor, fungus gardens swell with new growth, fed by the green tide above. The system hums, balanced on the edge of exhaustion and abundance, a machine built from flesh and instinct. In the world of leafcutter ants, survival does not belong to the strongest or the smartest. It belongs to the most organized. The air around the nest feels different before anything visible happens. A faint vibration hums through the space, not loud enough to hear, but strong enough to register in the body, like pressure building before a storm. The nest hangs from a branch or clings to the underside of a roof beam, its paper walls layered and fibrous, built from chewed wood and saliva hardened into a light but resilient shell. At a distance it appears fragile, almost temporary. Up close it radiates control. This is occupied territory, and everything within its invisible boundary is being watched. Wasps do not patrol their environment casually. They enforce it. Individuals hover at fixed distances from the nest entrance, their flight patterns tight and deliberate, wings beating fast enough to blur. Their compound eyes scan constantly, detecting movement far more efficiently than detail, tuned to identify approach trajectories rather than shapes. A bird passing overhead, a mammal brushing past foliage, or a human stepping too close triggers an immediate shift. Flight paths tighten. Antennae angle forward. The nest is no longer passive architecture. It becomes the center of a defensive network that can escalate from warning to violence in seconds. Territory for wasps is not defined by ownership of land, but by control of access to resources. The nest is the factory, the nursery, and the command center. Inside, larvae consume protein delivered by workers, converting it into growth that sustains the colony's future. Outside, workers forage for prey, sap, and nectar, navigating a landscape crowded with competitors. Any threat to this system, whether predator or rival, is treated as an existential risk. The response is calibrated accordingly. The first line of defense is signal, not force. Wasps advertise their presence with high contrast coloration, bands of yellow and black that cut sharply against natural backgrounds. This pattern is not camouflage, it is a warning, evolved through generations of predator learning. Birds that survive a wasp sting do not forget it. Mammals associate the coloration with pain almost instantly. The warning works because it is honest. The cost of testing it is too high. When proximity increases, chemical warnings join the visual display. Guard wasps release alarm pheromones from glands near the sting, saturating the air with a scent that carries both information and urgency. To other wasps, this signal means mobilization. To intruders, it goes unnoticed, which is precisely why it fails only once. A human may not smell the pheromone at all, but nearby wasps do, converging rapidly on the source. What appears to be a single insect reacting is, in fact, the visible edge of a coordinated response. If the intruder does not retreat, escalation is immediate. A wasp darts forward in a straight, aggressive line, not to sting yet, but to test reaction. This flyby is a final warning, an attempt to trigger withdrawal without expending venom or risking injury. Many predators learn here. Some do not. When the boundary is crossed, the strike is sudden and precise, driven by instinct sharpened through evolutionary trial. The sting itself is not a last resort. It is a tool optimized for reliability. Unlike bees, most wasps can sting repeatedly, their smooth stingers sliding in and out of tissue without tearing free. Venom is injected directly into muscle or skin, a complex cocktail of peptides and enzymes designed to cause immediate pain, disrupt nerve signaling, and trigger inflammation. The sensation is sharp and burning, not because the venom is lethal, but because pain is the objective. A predator that retreats alive spreads the lesson further than one that dies. Biologically, this makes sense. Killing is inefficient. Deterrence scales. The venom also carries alarm pheromones that mark the target chemically, turning the intruder into a beacon. Additional wasps lock onto the scent, striking the same location repeatedly. This is why swarms feel targeted rather than random. The wasps are not angry. They are following chemical gradients, reinforcing a defensive perimeter with overwhelming force. Inside the nest, the response continues. Workers fan their wings to ventilate and stabilize internal temperature, ensuring larvae are not overheated by the sudden activity. Others reinforce the entrance, clustering tightly to block access. The colony does not panic. It reallocates labor. Foraging may pause temporarily, but the nest remains operational. The system absorbs the disturbance and returns to equilibrium once the threat passes. Wasps also defend resources beyond the nest itself. Feeding sites, particularly those rich in protein, are guarded aggressively. A fallen piece of meat, a struggling insect, or sap leaking from damaged bark becomes a contested zone. Wasps arriving first establish dominance through posture and persistence, chasing away competitors with repeated charges. If resistance continues, stings follow. Ants, flies, and even other wasps are driven off through sheer escalation. Here, warning signals are minimal. The cost of losing the resource outweighs the risk of confrontation. Predator interactions reveal another layer of logic. Birds that specialize in catching insects often attempt to snatch wasps mid-flight, but many fail after early encounters. Some birds evolve techniques to neutralize the sting, crushing the wasp against branches or removing the abdomen before consumption. In response, wasps increase aggression near nests, reducing the chance of being isolated. Evolution shapes both sides, pushing tactics and counter-tactics forward in a constant feedback loop. The effectiveness of wasp defense lies not in individual strength but in speed and certainty. There is no hesitation phase. Once the threshold is crossed, the response is binary. This clarity is what makes warning signals effective only once. The system is designed so that ignoring the first message guarantees pain. Over time, predators learn to read the signs. Humans, less attuned to insect boundaries, often learn the same lesson abruptly. As the disturbance fades, the air settles. The nest resumes its low hum of activity. Wasps return to their posts, hovering, scanning, enforcing a border that exists only in behavior and chemistry. The paper walls remain intact, the larvae continue to feed, and the territory holds. In this world, survival does not depend on mercy or negotiation. It depends on rapid escalation, unambiguous signals, and a willingness to strike before the threat becomes real. The stillness arrives first, settling over the vegetation like a held breath. Leaves sway gently in the warm air, stems creak under their own weight, and insects move through the understory in a constant low-level churn of motion. Amid this activity, a shape waits. It is upright, angled slightly forward, forelegs folded close to the body as if in contemplation. The praying mantis does not blend in by disappearing completely. It blends in by becoming expected, a leaf that does not move, a stem that casts the right shadow, a silhouette that belongs so completely to the background that the eye stops questioning it. This predator is built for patience. Its body is elongated and narrow, compressing into the vertical architecture of plants. The thorax stretches like a hinge, allowing the head to pivot freely without shifting the rest of the body. This alone sets the mantis apart from most insects. Where others must turn their bodies to look, the mantis rotates its head in smooth arcs, scanning the environment with a precision that feels almost vertebrate. The compound eyes bulge outward, granting a wide field of view, but it is the overlap between them that matters most. This overlap creates depth perception, rare among insects, allowing the mantis to judge distance with lethal accuracy. Nothing about this animal is rushed. Metabolism runs efficiently but not explosively. The mantis can remain motionless for hours, sometimes days, waiting for the right alignment of chance and opportunity. This patience is not passive. Internally, muscles remain partially primed, tension stored in elastic structures within the thorax and forelegs. Sensory input continues uninterrupted. Antennae sample air currents. Eyes track movement patterns, filtering irrelevant motion from viable targets. Wind-driven leaf movement is ignored. The erratic flight of a fly is not. When prey enters the strike zone, the shift is instantaneous. There is no chase, no warning, no escalation. The mantis does not waste energy on pursuit because pursuit introduces variables. Instead, it allows prey to come close enough that escape becomes statistically unlikely. This is ambush warfare refined through millions of years of selection. Strength matters less than timing. Speed matters only at the moment it is applied. The strike itself is one of the fastest movements produced by an insect. The forelegs unfold in a fraction of a second, driven by powerful flexor muscles that have been held under tension. The motion is not a simple grab. It is a coordinated sequence where the legs snap forward, curve inward, and close simultaneously. Along the inner edges of these legs run rows of sharp spines, angled backward like barbs. These spines are not designed to pierce deeply but to trap. Once prey is caught between them, every attempt to pull free only drives it deeper into the grip. This spined grip is the mantis's true weapon. Many predators rely on venom, crushing force, or repeated strikes to subdue prey. The mantis relies on restraint. The grip immobilizes wings, legs, and body, preventing any effective counterattack. Insects that might otherwise bite, sting, or thrash are locked in place, their movements converted into leverage against themselves. The geometry of the grip ensures that even struggling prey remains pinned along the mantis's midline, directly beneath the head. Immediately after capture, the mantis adjusts its posture, bringing the prey closer to its mouthparts. The mandibles begin their work with calm efficiency, biting into soft tissue while the prey is still alive. There is no attempt to kill instantly. Instead, feeding begins at once, often starting with the head or thorax. This may appear brutal, but biologically it is efficient. Fresh tissue provides maximum nutritional value. Delaying feeding increases the risk of escape or interference by competitors. The mantis's digestive system is adapted for this style of feeding. Strong mandibles tear through exoskeletons that would challenge other predators. Salivary enzymes begin breaking down tissue even before ingestion, easing the load on the gut. Throughout the process, the forelegs maintain constant pressure, micro-adjustments compensating for any remaining movement. The prey's struggle ends quickly, not because it is killed immediately, but because it is rendered incapable of resistance almost from the moment of capture. This strategy allows mantises to target prey that might otherwise be dangerous. Wasps, bees, and even other mantises fall victim to the same method. The spined grip neutralizes stingers by pinning the abdomen. Wings are trapped before they can generate lift. In the rare cases where prey fights back successfully, Injuries to the mantis can be severe, which is why precision matters so deeply. A mistimed strike is costly. A correct one is decisive. The ecological role of the praying mantis is shaped by this efficiency. It is not a specialist predator tied to a single prey species. Instead, it is an opportunist capable of exploiting a wide range of insects and occasionally small vertebrates like lizards or frogs. This flexibility allows mantises to thrive in diverse environments, from tropical forests to temperate grasslands and gardens shaped by human hands. Wherever there is vertical structure and a steady flow of insects, the mantis can insert itself into the food web as a controlling force. Yet the mantis is not invincible. Its reliance on stillness makes it vulnerable to predators that detect shape rather than motion. Birds with keen eyesight can spot the outline of a mantis against foliage. Parasitic wasps lay eggs inside mantis egg cases, consuming the next generation before it ever emerges. Even within their own species, danger exists. Sexual cannibalism, where females consume males during or after mating, is not universal, but common enough to influence behavior. Males approach cautiously, often waiting until the female is distracted by feeding before attempting to mate. Here again, patience determines survival. The mantis also interacts subtly with its environment through thermoregulation. Its elongated body exposes a large surface area, allowing it to absorb heat efficiently in the sun. On cooler days, mantises reposition themselves to maximize solar exposure, raising body temperature to optimal levels for muscle performance. On hot days, they retreat into shade, reducing activity to prevent overheating. This behavioral regulation ensures that when the moment to strike arrives, the muscles will perform at peak speed. What makes the praying mantis unsettling is not just its violence, but its composure. There is no visible excitement, no escalation of behavior before the strike. The transition from stillness to action is absolute and irreversible. In a world where many predators rely on endurance, pursuit, or overwhelming force, the mantis demonstrates another path. Control the moment. Remove uncertainty. End the struggle before it truly begins. As the feeding concludes, fragments fall away to the forest floor, recycled almost immediately by ants and scavengers. The mantis cleans its forelegs meticulously, drawing each spine through its mouthparts to remove residue. Then it returns to stillness, folding its legs back into the familiar posture, merging once more with the vertical lines of its environment. To passing insects, it is just another leaf. To those that drift too close, it is the end of motion itself.
The surface of a sunlit wall, a tree trunk, or a broad leaf is never empty, even when it appears still. Micro-movements ripple across it constantly. Ants crossing invisible highways, flies landing and lifting again, mites navigating valleys between bark fibers. In this crowded, chaotic battlefield, one predator moves differently. It does not rush. It does not hide through stillness alone. Instead, it watches. The jumping spider occupies a world measured in angles and probabilities. Its body is compact, low to the surface, anchored by 8 legs that can shift direction instantly without changing posture. Unlike web-building spiders, it does not outsource violence to silk traps. It carries the hunt entirely within its nervous system. This is a predator defined not by strength or speed alone, but by perception. Its large forward-facing eyes dominate the face, glossy and dark, creating an unsettling impression of attention. These principal eyes provide acute visual resolution far beyond what most arthropods can achieve. They do not merely detect motion. They recognize shapes, track trajectories, and assess distance with precision that rivals small vertebrates. The environment around a jumping spider is saturated with competing signals. Wind moves shadows, leaves flicker, insects cross paths unpredictably. Yet the spider filters this noise with remarkable efficiency. Secondary eyes positioned around the head detect movement across a wide field, acting as early warning sensors. When motion triggers interest, the principal eyes lock on, narrowing focus. The spider pivots subtly, rotating its body in small increments, adjusting orientation without advancing. Every shift is deliberate. This is not stalking driven by hunger alone. It is calculation. Distance is everything.
A jump too short means exposure. A jump too long wastes energy and risks collision or misalignment. The spider gauges distance using motion parallax, tracking how objects shift relative to one another as it moves its head slightly from side to side. This head movement is so subtle it often goes unnoticed, but it is essential. Depth is reconstructed through these micro shifts, allowing the spider to build a three-dimensional model of its surroundings. In this moment, the spider is not reacting. It is simulating. Stalking begins once the target is identified as viable prey. The spider lowers its profile further, legs spreading slightly to distribute weight and stabilize posture. It advances in slow, uneven increments, pausing frequently. Each pause serves multiple purposes. It reduces detection by prey sensitive to vibration. It allows recalibration of distance. It conserves energy. The spider's body language changes as it moves, becoming less symmetrical, more angular, blending into the broken geometry of bark or stone. Camouflage here is not coloration alone. It is behavior. Prey insects often fail to recognize the threat because it does not behave like one. There is no pursuit, no direct line of approach. The spider circles, adjusting angle to avoid detection by compound eyes that favor wide lateral vision. It approaches from above or behind when possible, exploiting blind spots. Insects evolved to detect looming predators approaching head-on often miss the slow lateral advance of a jumping spider entirely. This is battlefield awareness expressed through evolution. At close range, the spider stops again. This pause is longer. Muscles load with stored energy as hemolymph pressure increases in the legs, preparing them for explosive extension. The spider's internal hydraulics are a critical part of the strike. Unlike mammals, spiders do not rely solely on muscle contraction to extend their limbs. Instead, they use fluid pressure to straighten the legs rapidly, allowing for sudden bursts of movement without bulky muscle mass. This system enables jumps that span many times the spider's body length with startling accuracy. But even now, the spider does not commit automatically. It reassesses. The prey shifts position. Wind changes direction. Another insect enters the field of view. The spider recalculates, adjusting its launch angle by fractions of a degree. Commitment only occurs when variables align. This is the spider's true advantage. Decision speed does not mean haste. It means knowing exactly when not to act. When the jump happens, it is instantaneous. There is no visible build-up, no warning. The spider launches itself through the air in a clean arc, legs extended forward, body aligned precisely with the target's center of mass. The trajectory is not random. It is pre-calculated, accounting for gravity, distance, and expected prey movement. Many jumping spiders even attach a silk dragline to the substrate before leaping, a safety tether that prevents catastrophic falls if the strike fails. This does not slow the attack. It simply reduces risk. Contact is brief and decisive. The spider lands directly on the prey, gripping it with the front legs while delivering a venomous bite. The venom is not designed for spectacle. It is efficient, rapidly immobilizing the nervous system of insects by disrupting ion channels and neuromuscular signaling. Struggle ends quickly. Unlike ambush predators that rely on restraint, the jumping spider relies on timing. The prey never has a meaningful chance to react. Once subdued, the spider retreats to a secure location to feed, often dragging prey many times its own weight across vertical surfaces with ease. Feeding is methodical. Digestive enzymes liquefy internal tissues, which are then consumed gradually. Throughout the process, the spider remains alert, rotating its body to monitor surroundings, secondary eyes scanning for threats or competitors. In this crowded environment, vulnerability never disappears. Ecologically, jumping spiders play a subtle but powerful role. They are generalist predators, regulating populations of flies, ants, mosquitoes, and other small arthropods. Their presence alters insect behavior. Prey species become more cautious in areas where jumping spiders hunt, changing movement patterns and feeding times. This ripple effect influences pollination, herbivory, and even plant growth at small scales. The spider's impact is not dramatic, but it is constant. The spider itself is prey to birds, lizards, and larger arthropods. Its defense lies not in armor or venom alone, but in awareness. Exceptional vision allows it to detect predators early. When threatened, it can leap in unpredictable directions, drop suddenly on silk lines, or retreat into narrow crevices. Some species even perform threat displays, raising forelegs and flashing iridescent mouthparts to confuse or deter attackers. These displays are not aggression. They are calculation under pressure. Thermoregulation also shapes the spider's daily rhythm. Being ectothermic, its performance depends on ambient temperature. In cooler conditions, movement slows and hunting pauses. In warmth, reaction times sharpen and jumps become more precise. Jumping spiders often position themselves in sunlit patches during the morning, absorbing heat to prime their systems, then retreat to shade as temperatures peak. This behavioral control ensures that when a hunt begins, the spider operates at peak efficiency. What makes the jumping spider remarkable is not just its ability to kill, but its ability to choose. In a world overflowing with targets and threats, it commits only when the outcome is nearly certain. This restraint is rare among predators. It reduces injury, conserves energy, and maximizes long-term survival. Strength can be countered. Speed can be matched. But perfect timing, informed by superior perception, is difficult to defeat. As the light shifts and shadows lengthen, the spider resumes its watch, perched on a ledge or leaf edge, eyes reflecting the world back in miniature. Around it, insects continue their restless movement, unaware of the calculations unfolding just centimeters away. In this battlefield of constant motion, the jumping spider does not dominate through force. It dominates through understanding. The forest canopy filters sunlight into heavy shafts that strike the trunks below, illuminating ridges of bark worn smooth by time and weather. High above the leaf litter, where branches narrow and pathways compress into natural bridges, another kind of battlefield emerges. Here, space is limited. Movement is constrained. Falling means disappearance. On these elevated corridors, rhinoceros beetles meet not as hunters or prey, but as rivals. The rhinoceros beetle is built for confrontation. Its body is compact and massively reinforced, wrapped in a thick exoskeleton that distributes force across rigid plates. The surface appears smooth and polished, but beneath it lies a lattice of internal supports designed to absorb impact without cracking. This armor is not passive defense. It is the foundation of a fighting system. Every curve, every ridge, every extension of the beetle's body contributes to leverage, balance, and control. Dominating the silhouette is the horn, or in some species, multiple horns branching from head and thorax. These structures are not weapons in the cutting sense. They do not pierce or slice. Instead, they act as levers, prying tools evolved to manipulate mass. The horn's shape varies across species, reflecting differences in fighting style and environment, but the principle remains constant. Victory comes from lifting, pushing, and flipping an opponent off the contested surface. Territory in this world is measured vertically. Sap flows higher up the tree. Females arrive to feed and mate along these routes. Males that control the narrow access points gain disproportionate reproductive advantage. The result is intense competition, focused on specific locations rather than broad areas. The bark ridge becomes an arena, the branch junction becomes a gate. These are choke points where strength and technique matter. Encounters begin with assessment. Two beetles approach each other slowly, antennae probing, legs gripping the uneven surface. There is no immediate charge. Each individual adjusts stance, lowering its center of mass and aligning its body with the curve of the bark. The beetles angle their horns, testing reach and fit. At this stage, the contest is still flexible. A weaker male may retreat without physical contact, conserving energy and avoiding injury. This restraint is adaptive. Exoskeletons are strong, but damage is costly and slow to repair. When neither retreats, contact begins. Horns lock together with a dull scrape, chitin against chitin. The beetles push forward, legs digging in, claws hooking into microscopic cracks in the bark. This is not raw strength alone. It is physics. Each beetle seeks to position its horn beneath the opponent's center of mass while keeping its own body anchored. The narrowness of the surface amplifies the stakes. There is no room to circle, no flanking maneuver. The fight compresses into a linear struggle. Muscles in the thorax contract with sustained force, transmitting power through the horn. The beetle does not jerk or strike. It applies steady pressure, attempting to lift. The opponent counters by lowering its body, spreading its legs wider to increase friction and stability. Tiny adjustments make the difference between balance and collapse. A slip of one claw can shift weight enough to allow the horn to slide underneath, levering the body upward. When leverage is achieved, the contest accelerates. One beetle heaves, lifting the other partially off the bark. Gravity becomes an ally. The lifted beetle thrashes, legs scraping for purchase, but the horn's curve channels movement upward and outward. A final push sends the loser tipping sideways, tumbling into the air. There is no killing blow. Defeat is measured in distance fallen. A beetle that drops several meters to the forest floor may survive, but it is removed from the contest, forced to climb again through a gauntlet of competitors. This fighting style explains the exaggerated horns seen in dominant males. Larger horns provide greater mechanical advantage, allowing smaller force inputs to generate larger lifting effects. However, horns are expensive. They require significant energy to grow and increase overall body mass, which can reduce mobility and increase predation risk. This trade-off shapes the population. Not all males develop massive horns. Some adopt alternative strategies, sneaking past dominant males to mate with females while avoiding combat altogether. This coexistence of strategies reflects frequency-dependent selection, where success depends on how common each approach is within the population. The beetle's physiology supports these prolonged contests. Unlike predators that rely on short bursts of speed, rhinoceros beetles generate sustained force. Their muscles are adapted for endurance, fueled by efficient metabolic pathways that resist rapid fatigue. Hemolymph circulates through the body, distributing heat generated during exertion. The exoskeleton itself aids thermoregulation, radiating excess heat into the surrounding air. Fights often occur during cooler nighttime hours, when temperatures reduce the risk of overheating and predators are less active. Sensory input during combat is limited but sufficient. Vision plays a minor role. The beetles rely more on tactile feedback, sensing pressure through the horn and legs. Mechanoreceptors embedded in the exoskeleton detect strain and slippage, allowing rapid adjustment of force and posture. Chemical cues also influence behavior. Pheromones released by females draw males into contested zones, while the presence of other males increases aggression thresholds. The arena is not random. It is chemically marked and biologically primed for conflict. Predators watch these contests from the shadows. Birds, mammals, and reptiles are drawn to the noise and movement, exploiting distracted beetles. This pressure adds urgency to the fights. Prolonged grappling increases vulnerability, favoring individuals that can resolve contests quickly through superior leverage rather than drawn-out pushing matches. Efficiency once again determines survival. When a dominant male secures a territory, it positions itself at the narrowest point, blocking passage. Incoming rivals are challenged immediately. Females arriving to feed are allowed through, sometimes escorted, sometimes ignored. Mating occurs nearby, often on the same bark surfaces where battles were fought moments earlier. The arena never rests. Control must be constantly reinforced. The fallen beetles below do not disappear from the system. They feed, recover, and attempt to climb again, sometimes choosing different routes or times to avoid the dominant male. The population remains dynamic, with dominance shifting as individuals age, sustain damage, or exhaust resources. The forest, vast and layered, supports countless such arenas simultaneously, each hosting its own silent tournaments. What makes Rhinoceros Beetle combat compelling is its clarity. There is no deception, no ambush, no chemical warfare. Victory comes from understanding leverage, balance, and timing. The beetles do not fight to destroy each other. They fight to displace, to remove, to claim position. On a narrow bridge of bark suspended above the forest floor, that distinction is everything. As night deepens, the sounds fade. The winners remain, anchored and still, horns angled forward like living barricades. Below them, the forest continues its endless motion. Leaves fall, insects move. Somewhere, another arena is forming, and another contest of armored wrestlers is about to begin. The air beneath the canopy cools as evening approaches, and the forest shifts into a different rhythm. Sap begins to flow more freely along wounded bark, fermenting slightly as sugars rise toward the surface. The scent carries far in the stillness, drawing in creatures attuned to opportunity. Along the trunks of old trees and the fallen giants decomposing on the forest floor, heavy shapes begin to climb. Their movement is deliberate, almost ceremonial, each step anchored with care. This is the domain of the stag beetle, and here, gravity decides everything. Stag beetles do not fight in open space. Their battles are confined to vertical worlds, where surfaces narrow, angles steepen, and mistakes are punished instantly. Tree trunks, sap runs, and broken branches become contested platforms, elevated above the ground where access is limited and retreat is costly. The beetle's body reflects this reality. Broad, flattened, and reinforced, it is designed to press tightly against surfaces, maximizing friction and stability. Thick legs end in strong claws that hook into bark, turning rough texture into grip. Every movement acknowledges the pull of gravity, not as a threat to be avoided, but as a force to be exploited. The most striking feature of the stag beetle is its mandibles, elongated and curved like antlers, projecting forward with unmistakable intent. These are not jaws meant for chewing through tough material. They are specialized grappling tools, shaped to grasp, lift, and displace. The inner edges are often lined with small teeth or ridges, improving purchase on an opponent's body. The mandibles open wide, creating a frame within which another beetle can be captured. Once engaged, they function less like pincers and more like lifting forks, designed to lever an opponent upward and away from the surface. Encounters begin with convergence. Two males approach the same sap flow or climb toward the same elevated route, drawn by chemical cues released by feeding beetles and receptive females. The air around these sites is saturated with information. Antennae sample scent continuously, confirming the presence of rivals before they are seen. When visual contact is made, both beetles slow, adjusting posture and spacing. There is no sudden charge. Instead, they align themselves carefully, ensuring footing before committing to contact. On a vertical surface, balance is as important as strength. When mandibles meet, the sound is a dull click, followed by the scrape of chitin against chitin. The beetles lock together head to head, bodies pressed close to the bark. Muscles in the head and thorax contract, generating force not to crush, but to lift. Each beetle attempts to slide its mandibles beneath the opponent's body, seeking leverage rather than penetration. Success depends on angle. A slight elevation of the head, a subtle shift of the legs, can create an opening just wide enough to tip the balance. Gravity waits patiently. The moment one beetle's feet lose full contact with the bark, the contest tilts sharply. Even partial lift reduces friction, weakening the opponent's ability to resist. The attacking beetle increases pressure, raising its head and pulling upward. The mandibles act as a fulcrum, transferring force efficiently through the rigid exoskeleton. This is where size matters, but technique matters more. A smaller beetle with superior positioning can unseat a larger rival by exploiting the geometry of the surface. Once an opponent is lifted clear, the outcome is nearly inevitable. The beetle twists slightly, redirecting force sideways. Gravity takes over, pulling the lifted body away from the trunk. Legs scramble briefly, claws scraping for purchase that no longer exists. Then the grip breaks, and the defeated beetle drops into open space. The fall may only last seconds, but at insect scale, distance magnifies consequence. Impact with the forest floor can damage limbs, disorient sensory systems, or simply remove the beetle from the competitive zone long enough for dominance to be established above. This is why falling functions as a knockout. Death is not required. Displacement is enough. A beetle that must climb again spends energy, risks predation, and may arrive to find the resource already controlled. In evolutionary terms, gravity becomes a weapon wielded indirectly, its force harnessed through morphology and behavior. The victor remains anchored to the surface, conserving energy and maintaining position. The physiology of the stag beetle supports this demanding style of combat. The neck region is heavily reinforced, allowing the head to bear substantial loads without injury. Muscles controlling the mandibles are among the strongest in the insect world relative to body size, capable of generating force sufficient to lift objects many times the beetle's own weight. Yet these muscles are not built for speed. They apply steady, controlled power, ideal for prolonged grappling rather than quick strikes. Thermoregulation plays a subtle role in these encounters. Stag beetles are most active during cooler evening hours, when lower temperatures prevent overheating during sustained exertion. Their dark coloration absorbs residual warmth from the bark, maintaining muscle efficiency as ambient temperatures drop. During the heat of the day, activity decreases, and beetles retreat into crevices or beneath loose bark, conserving energy and avoiding desiccation. Predators exploit these battles whenever possible. Birds and mammals learn to watch sap flows and elevated roots, recognizing them as predictable gathering points. A beetle distracted by combat is less likely to detect approaching danger. This pressure favors individuals that resolve contests quickly, using decisive lifts rather than extended pushing matches. Again, efficiency shapes behavior. The longer a fight lasts, the greater the risk to both participants. Not all males fight in the same way. As with many species where exaggerated weapons evolve, alternative strategies persist. Some males possess smaller mandibles and avoid direct confrontation, instead sneaking past dominant individuals during moments of distraction. These beetles may mate without ever engaging in combat, trading physical power for timing and caution. The population maintains this balance because no single strategy dominates under all conditions. Dense competition favors strength. Sparse competition favors stealth. Females, lacking the massive mandibles of males, move through this world differently. They feed and select mates among the dominant individuals, but their presence intensifies conflict. Chemical signals released by females increase aggression among nearby males, raising the frequency and intensity of grappling encounters. The arena becomes charged, each contest reinforcing the hierarchy that determines reproductive success. The forest floor below tells a quieter story. Fallen beetles crawl among leaves and roots, feeding, recovering, and preparing to climb again. Some bear scars, chipped mandibles or damaged legs, reminders of previous defeats. These injuries influence future behavior, making individuals more cautious or forcing them into alternative strategies. Survival continues, even after loss. What defines the stag beetle is not cruelty, but mechanical clarity. Its battles are resolved through physics rather than injury, through displacement rather than destruction. Gravity is ever present, impartial and absolute, waiting to reward precision and punish error. On a vertical battlefield where footing is everything, the beetle that best understands leverage controls the outcome. As darkness deepens and the forest settles, silhouettes cling to trunks and branches, mandibles open, bodies pressed close to the bark. Somewhere above the ground, another grapple begins, chitin locking, muscles straining, gravity poised to decide the winner. In this world, brutality does not roar or bleed, it simply lets go. The forest does not advertise its strongest defenses. They are hidden beneath bark, sealed inside timber, and buried deep within structures that appear inert and unoccupied. Fallen trunks lie scattered across the forest floor, their surfaces cracked and softened by moisture, fungi, and time. Standing trees bear scars from storms and animals, wounds that leak sap and invite decay. To most predators, these are feeding grounds, places where life is exposed and accessible. To the Longhorn Beetle, they are fortresses. Adult Longhorn Beetles arrive quietly. Their elongated bodies and impossibly long antennae give them an almost skeletal silhouette as they crawl across bark or settle into crevices. The antennae sweep constantly, sampling chemical signals that reveal the condition of the wood beneath their feet. These beetles are not searching for food alone. They are evaluating construction sites, moisture content, fungal activity, wood density, and species identity all matter. The future of the next generation depends on choosing the right structure, one that will support life hidden from the violence of the outside world. Once a suitable site is found, the adult stage performs its role quickly. Eggs are deposited into cracks, under bark flakes, or directly into shallow pits, chewed into the wood. The adult's involvement ends here. There will be no guarding, no provisioning, no return. Survival is entrusted entirely to architecture. When the larvae hatch, they do not emerge into the open forest, they turn inward. The larval stage of the Longhorn Beetle is pale, soft, and vulnerable by design. Legs are reduced, vision is absent, and the body is optimized not for movement across surfaces, but for pushing forward through resistance. Powerful mandibles dominate the head, shaped to grind wood fibers into fine particles. From the moment the larva begins feeding, it also begins building. Every bite excavates a tunnel. Every tunnel deepens the fortress. Wood is not a uniform material. It is layered, fibrous, reinforced by lignin, and often inhabited by fungi that alter its structure. Longhorn beetle larvae exploit this complexity. They follow grain lines, avoid denser knots, and sometimes track fungal growth that softens wood chemically before it is consumed mechanically. The result is an expanding network of galleries hidden entirely from view. From the outside, the tree appears unchanged. Inside, it is being reshaped into a labyrinth. This hidden life stage transforms the rules of survival. Most insect larvae exist in exposed environments where speed, camouflage, or chemical defenses determine survival. Longhorn beetle larvae remove themselves from this equation entirely. Predators cannot see them. Parasites struggle to reach them. Environmental extremes are buffered by the surrounding wood, which insulates against temperature fluctuations and retains moisture. The forest may freeze, burn, flood, or dry, but inside the timber, conditions remain relatively stable. This protection reshapes predator behavior. Birds that specialize in extracting insects from wood, such as woodpeckers, are among the few capable of breaching these defenses. Their beaks strike with tremendous force, chipping away bark and splintering wood to reach hidden prey. Yet even here, success is not guaranteed. Larval tunnels can extend deep into the trunk, beyond the reach of repeated strikes. The energy cost of excavation is high, and predators must choose targets carefully. A single misjudgment wastes time and exposes the predator to its own risks. Mammals face similar challenges. Rodents gnaw at decaying logs, tearing away layers to uncover larvae, but dense or living wood resists them. Insects that parasitize other insects are largely excluded from this environment. Their ovipositors are often too short to reach deeply buried larvae, and chemical cues dissipate through layers of wood, making precise targeting difficult. The fortress does not make the larvae invincible, but it shifts the odds dramatically in their favor. Inside the tunnel system, the larva grows slowly but steadily. Digestion is aided by symbiotic microorganisms in the gut, capable of breaking down cellulose and lignin into usable nutrients. Without these microbes, the larva would starve inside a world of inedible material. This partnership allows longhorn beetles to exploit a resource most animals cannot, turning dead or dying trees into both shelter and sustenance. The forest's decay becomes fuel for new life. The architecture of the tunnels evolves as the larva grows. Early galleries are narrow, conserving energy and minimizing exposure. As the larva increases in size, tunnels widen, sometimes branching or looping back toward the surface. Waste material, known as frass, is packed behind the larva or pushed into side chambers, keeping the main tunnel clear. This housekeeping behavior reduces the risk of fungal overgrowth or bacterial infection that could compromise the fortress from within. Time stretches differently inside wood. The larval stage can last years, depending on species, climate, and wood quality. This extended development reduces the urgency of growth, allowing the beetle to synchronize emergence with favorable conditions. While outside ecosystems fluctuate rapidly, the fortress buffers change. This temporal insulation is as important as physical protection. Predators cannot target what does not appear. Eventually, transformation begins. Deep within the wood, the larva constructs a pupal chamber, sealing itself off completely. Here, it will reorganize its entire body, dissolving larval tissues and rebuilding into the adult form. During this period, vulnerability peaks. Movement stops, feeding ceases, yet the fortress remains intact. The surrounding wood absorbs shock, muffles vibration, and blocks intrusion. Predators searching the surface have no indication that anything has changed inside. When the adult beetle finally emerges, it does so with purpose. Mandibles chew a clean exit tunnel to the surface, often timed to coincide with warm temperatures and peak mating opportunities. The sudden appearance of a large beetle from seemingly solid wood can feel uncanny, a reminder that the forest hides processes unfolding on timescales and in dimensions we rarely perceive. The adult stage re-enters a more dangerous world. Exposed, mobile, and conspicuous, the beetle must now contend with birds, reptiles, and mammals directly. Its armor is thicker, its flight muscles strong, its antennae alert to chemical signals, but the most dangerous phase of life has already passed. The war was fought underground, won through architecture rather than combat. Ecologically, longhorn beetles play a dual role. Their tunneling accelerates wood decomposition, allowing fungi and microbes to penetrate deeper into trees and logs. This process recycles nutrients back into the soil, supporting plant growth and sustaining forest productivity. At the same time, excessive infestation can weaken living trees, altering forest structure and creating openings in the canopy. These changes ripple outward, influencing light availability, species composition, and habitat complexity. The fortress strategy also shapes evolutionary pressures on predators. Those capable of breaching wood gain access to a rich, stable food source, driving adaptations in strength, tool use, and sensory perception. The arms race shifts from speed and venom to endurance and excavation. The battlefield is no longer the forest floor or open air. It is the interior of trees. What defines the longhorn beetle is not aggression, nor speed, nor deception. It is foresight embedded in biology. By relocating its most vulnerable life stage into a structure that predators cannot easily penetrate, the species changes the terms of conflict entirely. Survival is achieved not by fighting harder, but by becoming unreachable. As night settles over the forest and sounds fade into layered silence, logs lie motionless and trunks stand unchanged. Yet inside them, lives continue, jaws grinding softly, tunnels extending millimeter by millimeter. The war has not ended. It has simply moved somewhere predators cannot follow. At the edge of a still pond, where reflections lie unbroken, and the boundary between air and water appears calm and absolute, another kind of territory begins. It is neither solid nor liquid in the way the eye expects. It is a surface, a thin elastic membrane formed by molecular attraction, capable of bearing weight only under precise conditions. To most animals, it is a barrier. To the water strider, it is a battlefield. Gerridae arrive without splash or announcement. Long legs touch down lightly, dimpling the surface without breaking it, each contact point creating a small depression that vanishes almost instantly. The insect's body remains elevated above the water, supported not by buoyancy but by physics. Surface tension holds firm, reinforced by a dense forest of microscopic hairs coating the legs, each hair angled and waxed to repel water. Air becomes trapped among them, forming a cushion that prevents wetting. The strider does not float. It stands. The water surface, viewed from above, appears uniform. To the water strider, it is textured and alive with information. Every disturbance sends waves outward, ripples carrying data about size, speed, and direction. A struggling insect generates a chaotic pattern. A rival strider produces a sharp, rhythmic signal. Wind draws long, low oscillations across the pond. The strider's sensory world is built around detecting these movements. Specialized mechanoreceptors in the legs register minute vibrations, allowing the insect to read the surface as clearly as a hunter reads tracks in soil. Territory here is fluid, constantly shifting with light, wind, and prey availability. Water striders patrol defined sections of surface, moving in looping paths that intersect and overlap. Dominant individuals claim the most productive zones, often near vegetation where insects fall into the water or emerge from below. Control is enforced not through physical barriers, but through signaling. When another strider enters a claimed area, the response is immediate. The resident generates a series of deliberate ripples by tapping or vibrating its legs against the surface. These waves travel outward in expanding circles, intersecting with the intruder's position. To an untrained eye, nothing happens. To the insects, this is confrontation. The ripple pattern communicates presence, size, and intent. A weaker or smaller strider often retreats without contact, gliding away on rapid strokes that push backward against the surface. The water never breaks. The message is received and obeyed. When neither yields, escalation follows. Physical encounters are brief and precise. The insects rush toward each other, legs skimming the surface, bodies remaining elevated. They grapple momentarily, forelegs reaching to hook or shove. The goal is not injury, it is displacement. One strider attempts to force the other into unstable positions where surface tension can no longer support weight evenly. A misstep causes a leg to pierce the surface, breaking the delicate balance. The submerged limb creates drag, slowing movement and compromising control. In these moments, defeat arrives swiftly. The compromised insect retreats or risks drowning if unable to recover footing. The effectiveness of this strategy depends entirely on physics. Surface tension provides support only when force is distributed across sufficient area. Water striders exploit this by having legs far longer than their bodies, spreading weight across multiple contact points. Each leg presses down lightly, creating dimples rather than punctures. Rapid movement is achieved through rowing motions, legs pushing backward to generate thrust while maintaining contact with the surface. Turning involves asymmetric strokes, altering force distribution with fine precision. Feeding occurs within this contested space. Prey arrives unpredictably, falling from overhanging vegetation or emerging from the water as aquatic insects complete their life cycles. A struggling insect trapped on the surface creates frantic ripples that radiate outward, advertising vulnerability. Water striders detect these signals almost instantly. The nearest individual rushes toward the disturbance, navigating the wave patterns to locate the exact position of the prey. Capture is efficient. The strider pierces the prey with a sharp proboscis, injecting enzymes that begin external digestion. Fluids are drawn out while the prey remains immobilized, pinned against the surface by the predator's legs. This feeding method minimizes effort and exposure. The prey cannot escape into the air or water. It is trapped at the boundary. Competition for such opportunities is intense. Multiple striders may converge on the same prey, triggering rapid ripple-based confrontations. The individual that maintains control of the surface around the prey usually wins, using wave signals to repel competitors while feeding continues. Here, control of physics directly translates to access to energy. Whoever dominates the surface dominates the food supply. Predators challenge this system from above and below. Fish rise from beneath the surface, attempting to snatch striders with sudden lunges. Birds strike from the air, aiming to pluck insects cleanly without disturbing the water. The strider's defense lies in awareness and speed. The same sensory system used to detect prey also detects threats. The approach of a fish creates pressure waves that distort surface patterns. A bird's shadow alters light and triggers escape responses. In both cases, the strider can accelerate instantly, skimming away before contact. Thermoregulation influences patrol patterns and activity levels. Being ectothermic, water striders rely on ambient temperature to maintain muscle performance. Morning sun warms the surface layer of water, increasing activity as metabolic processes speed up. During peak heat, individuals may reduce movement, seeking shaded areas to avoid overheating. The water itself acts as a thermal buffer, moderating temperature extremes and allowing prolonged activity compared to terrestrial surfaces. Reproduction adds another layer of complexity. Males use ripple signals not only to defend territory, but also to attract females. Courtship involves generating specific wave patterns that differ from aggressive signals in frequency and rhythm. Females evaluate these patterns, assessing the male's size and fitness indirectly through the energy and consistency of the ripples produced. This communication system allows mating decisions to occur without direct contact, reducing risk in a crowded environment. Eggs are laid on floating or emergent vegetation, anchoring the next generation close to the surface world they will inherit. Nymphs hatch already adapted to surface life, their legs coated in hydrophobic hairs from the start. They grow through successive molts, each stage refining control over balance and movement. From early life onward, the surface is both home and hazard. Ecologically, water striders regulate populations of insects that interact with aquatic systems, linking terrestrial and aquatic food webs. By preying on insects that fall into water or emerge from it, they influence nutrient flow between environments. Their presence alters behavior in both prey and predators, creating feedback loops that shape community dynamics at the water's edge. What makes the water strider remarkable is not simply its ability to stand on water, but its mastery of a domain defined by invisible forces. It patrols a territory that exists only because of molecular attraction, communicates through waves that vanish almost as soon as they form, and enforces dominance without walls or weapons. The battlefield is ephemeral, constantly reshaped by wind, rain, and motion. Yet control persists, moment by moment, maintained through precision and perception. As evening falls and the surface darkens, ripples become harder to see, but no less meaningful. Striders continue their patrols, legs tracing patterns across the water, reading and writing information into a medium most creatures never notice. In this world, land and water are irrelevant. Only the surface matters. Whoever controls it controls survival. Morning light reaches the wetland in narrow bands, catching on reeds and drifting mist, illuminating a space that never truly rests. The air above the water is already occupied. Small insects rise from the surface in uneven pulses, midges and flies lifting into the warming air, tracing invisible currents that form and collapse with the slightest change in temperature. To most creatures, this is background motion. To the Scarlet Dragonfly, it is a living map. The dragonfly arrives not by chance, but by patrol. Its body cuts cleanly through the air, wings beating in a steady rhythm that seems effortless, yet precise. The scarlet abdomen glows against the muted greens and browns of the wetland, not as a warning, but as a declaration of presence. This is controlled airspace. Unlike ambush predators that wait for prey to stumble close, the dragonfly claims volume. It does not defend a point. It defends a three-dimensional corridor of sky. Flight defines everything about this animal. The wings are long, narrow, and driven independently, each capable of adjusting stroke angle, amplitude, and timing. This independence allows the dragonfly to hover, accelerate, decelerate, and pivot without changing body orientation. Lift and thrust are separated functions, managed dynamically in response to the surrounding air. What appears smooth to the eye is, in reality, a constant series of micro-corrections, each wing responding to subtle changes in airflow. Vision anchors this system. The dragonfly's compound eyes dominate the head, wrapping around it until almost nothing escapes their field. Each eye contains thousands of individual lenses, tuned not for fine detail, but for motion detection and contrast. Together, they provide nearly complete visual coverage, eliminating blind spots that predators often exploit. Movement anywhere within this sphere is registered instantly, categorized, and tracked. Hunting begins with assessment. The dragonfly cruises along established routes, following the edges of vegetation, the margins of open water, and the invisible boundaries where insect traffic concentrates. It does not chase everything it sees. Instead, it selects targets based on size, speed, and trajectory. A fly drifting aimlessly is ignored. A midge accelerating upward catches attention. The dragonfly's brain calculates interception paths automatically, solving a moving geometry problem in real time. Unlike pursuit predators that follow behind prey, the dragonfly intercepts. It predicts where the prey will be, not where it is. Once a target is selected, the dragonfly alters its flight path subtly, adjusting speed and angle, so that both predator and prey converge at a single point in space. This minimizes energy expenditure and maximizes success. The prey never sees the approach from behind. It collides with the predator's trajectory. The final approach is nearly silent. Wing beats change frequency, reducing turbulence that might alert sensitive insects. The dragonfly accelerates sharply, closing distance in fractions of a second. Legs extend forward, forming a basket lined with spines. This structure is not used to grab after contact, but to ensure that contact results in capture. The prey strikes the basket mid-flight, trapped instantly. There is no struggle. The collision itself ends the encounter. Mid-air feeding often begins immediately. The dragonfly transfers prey to its mandibles without landing, biting and consuming while still in flight. This ability reduces vulnerability, allowing continuous patrol without interruption. When prey is larger or handling time increases, the dragonfly may perch briefly, selecting exposed stems that provide clear takeoff paths. Even at rest, the eyes continue scanning, tracking movement beyond the field of view of most predators. Agility gives the dragonfly dominance in this environment. Sharp turns are executed through rapid adjustments in wing phase, allowing the insect to pivot around its center of mass. It can reverse direction almost instantly, perform vertical climbs, or drop suddenly to avoid threats. These maneuvers are not reactions alone. They are anticipatory, informed by constant sensory input and internal models of motion. Other aerial predators share this space, but few can match the dragonfly's control. Birds may pass through, snatching insects opportunistically, but their size and momentum limit precision. Bats hunt at night, using echolocation to detect prey invisible to sight, but they operate in a different temporal niche. During daylight, the dragonfly reigns. Competition among dragonflies themselves is intense. Territories overlap along productive stretches of water, and individuals enforce boundaries through aerial displays. Rivals engage in high-speed chases, spiraling upward or racing parallel along invisible lines. These contests test endurance and maneuverability rather than strength. The individual that maintains position longest retains control. Losers retreat, conserving energy for less contested zones. Reproduction intertwines with air dominance. Males patrol territories attractive to females, using aerial performance as a signal of fitness. The ability to hold a zone, intercept prey efficiently, and repel rivals demonstrates mastery of the air. Females arriving to mate evaluate these cues indirectly, selecting partners that control the best hunting grounds. Eggs are laid in or near water, often inserted into plant tissue, anchoring the next generation to the same aerial corridors. The dragonfly's life cycle spans two worlds. Beneath the water, the larval stage lives as a separate predator entirely, equipped with extendable jaws and adapted to ambush aquatic prey. This phase can last years, shaped by water temperature, oxygen levels, and prey availability. When emergence occurs, the larva climbs from the water, splits its skin, and unfolds wings that must harden quickly. Survival depends on speed. Vulnerability peaks during transformation, but once airborne, the dragonfly transitions into a different kind of hunter. Thermoregulation governs flight capacity. Being ectothermic, the dragonfly relies on environmental heat to power muscle activity. Early mornings are spent basking, wings angled to absorb sunlight. As temperature rises, flight becomes more frequent and aggressive. In extreme heat, activity may decrease, with individuals retreating to shade to prevent overheating. This rhythm shapes daily hunting patterns and influences interactions with prey populations that respond to the same thermal cues. Predators of dragonflies exist, but few succeed consistently. Birds capable of catching dragonflies in flight must anticipate their erratic turns. Spiders build webs along flight paths, occasionally ensnaring the unwary. Fish leap from the water, targeting low-flying individuals. Each threat reinforces the importance of altitude control, speed, and unpredictability. The dragonfly survives not through armor or venom, but through mastery of movement. Ecologically, scarlet dragonflies exert strong top-down control on flying insect populations. By removing large numbers of mosquitoes, midges, and flies, they influence disease dynamics, pollination rates, and nutrient cycling. Their presence alters the behavior of prey species, which may shift activity times or flight paths to reduce risk. These changes ripple outward, shaping the structure of the wetland community. What makes the scarlet dragonfly's hunting brutal is not violence, but inevitability. Prey is not chased into exhaustion or cornered into submission. It is intercepted, removed from the air without warning. There is no signal to interpret, no chance to flee. The attack arrives fully formed, the result of calculations completed before the prey is even aware it has been selected. As the day advances and light intensifies, the wetland fills with motion. Insects rise and fall, birds pass overhead, ripples spread across the water's surface. Through it all, flashes of red trace precise paths through the air, looping, turning, accelerating. The dragonfly does not dominate through force alone. It dominates by understanding the medium it inhabits more completely than anything else around it. In the open sky above the water, efficiency is survival, and hesitation is extinction. Night does not fall all at once in the desert or dry woodland. It arrives gradually, draining color from the landscape until shapes soften and distances collapse. Heat bleeds slowly from rocks and soil, rising in invisible currents that carry scent and vibration across the ground. What was hostile under the sun becomes active after dark. This is when the black scorpion emerges, not as a shadow moving through darkness, but as a system tuned to it. The scorpion's body is low and compact, pressed close to the substrate as it advances. Each step is measured, the legs spreading outward to maximize contact with the ground. Vision plays only a supporting role here. In the absence of light, sight is unreliable, but the scorpion does not rely on it. Instead, the world arrives through vibration. Every movement in the environment, from the footfall of a beetle to the brush of a rodent's tail, sends ripples through sand and stone. To most animals, these signals are lost in noise. To the scorpion, they are precise coordinates. Specialized sensory organs called slit sensilla line the legs and body, microscopic cracks in the exoskeleton that deform under pressure. These structures detect minute changes in vibration and substrate strain, translating them into information about direction, distance, and even mass. A heavy prey item produces a different vibrational signature than a light one. The frequency, amplitude, and timing of each wave matters. The scorpion's nervous system integrates these signals rapidly, building a spatial map of its surroundings without ever seeing them. Positioning is everything. The scorpion does not wander aimlessly through the night. It selects ambush sites with care, often near rocks, burrow entrances, or vegetation where prey traffic concentrates. Here, vibrations are channeled and amplified, making detection easier. The scorpion aligns its body so that incoming signals reach its legs symmetrically, allowing more accurate triangulation. It settles into stillness, tail arched loosely over the body, pedipalps held slightly open. This posture is not passive, it is readiness. Prey approaches unaware. A cricket hops nearby, its movement sending sharp rhythmic pulses through the ground. The scorpion remains motionless, filtering the signal. Distance decreases, direction stabilizes. The prey pauses, then moves again. The scorpion adjusts internally, shifting weight almost imperceptibly to refine its map. Darkness hides nothing here. It clarifies. When the prey enters range, the attack unfolds in a precise sequence refined by evolution. The first motion is forward and lateral, a sudden surge that closes distance before the prey can register danger. The pedipalps snap shut around the target, thick claws lined with textured surfaces that increase grip. This clamp is not meant to crush. It is meant to immobilize. Legs and wings are pinned, escape routes vanish. Only after control is established does the tail come into play. The metasoma, often described simply as the tail, is a segmented muscular structure capable of rapid, controlled movement. It arcs forward in a smooth, practiced motion, the stinger aligning with soft tissue. The sting itself is quick and deliberate, delivering venom directly into the prey's body. This venom is a complex mixture of neurotoxins and enzymes, varying between species but generally optimized to disrupt nerve transmission rapidly. The timing matters. By clamping first, the scorpion minimizes the risk of counterattack. Many nocturnal insects possess their own defenses, spines, mandibles, or chemical sprays. Immobilization neutralizes these threats before venom is deployed. The result is efficiency. The prey's struggle ends quickly, not through prolonged combat, but through a coordinated sequence where each action sets the stage for the next. Feeding follows with similar restraint. The scorpion uses its mouthparts to tear and liquefy tissue, ingesting nutrients slowly. Digestion begins externally, enzymes breaking down prey tissues before ingestion. Throughout the process, the scorpion remains alert, legs still in contact with the ground, continuously sampling vibrations. Even while feeding, it does not relinquish awareness of its surroundings. Night is crowded with dangers as well as opportunities. Predators of scorpions include mammals, birds, reptiles, and even other arthropods. Some rodents learn to strike quickly, targeting the tail to avoid being stung. Certain owls prey on scorpions with practiced precision, relying on silent flight and acute hearing. The scorpion's defense against these threats lies again in its sensory map. Vibrations from approaching predators differ from those of prey in both scale and pattern. Heavier footfalls, longer wavelengths, irregular timing all signal danger. The scorpion responds by freezing, retreating into cover, or raising its tail in warning posture. Thermoregulation plays a subtle but crucial role in this nocturnal life. During the day, the black scorpion shelters under rocks or in burrows, avoiding lethal heat and desiccation. These refuges maintain more stable temperatures and humidity levels, protecting delicate tissues and preventing water loss. At night, cooler air allows safe activity. Muscle performance improves as body temperature stabilizes within an optimal range. Movement becomes more precise. Sensory processing sharpens. Reproduction also unfolds under cover of darkness. Courtship in scorpions is a careful dance, guided by chemical cues and tactile signals rather than sight. Males and females engage in a controlled interaction, grasping pedipalps and maneuvering together as the male positions the female over a deposited spermatophore. This process requires coordination and trust in a world where misinterpretation can be fatal. Even here, vibration and touch dominate communication. Young scorpions are born live, climbing onto the mother's back where they remain through their first molt. During this time, the mother's movements slow, her posture protective. Vibration sensing extends beyond herself to the fragile offspring she carries, influencing how and when she moves. Survival at this stage depends entirely on remaining undetected. Ecologically, black scorpions regulate populations of nocturnal insects and small arthropods, shaping the balance of desert and dry woodland ecosystems. Their presence influences prey behavior, altering movement patterns and activity times. They also serve as prey themselves, transferring energy up the food chain. The night economy depends on such exchanges, invisible by day, but constant and essential. What defines the scorpion's warfare is not aggression, but perception. It does not dominate through speed alone or overwhelming force. It dominates by knowing where everything is, even when nothing can be seen. Darkness does not limit the scorpion. It transforms the world into a sensory map, each vibration a data point, each movement a signal to be interpreted. As the night deepens, stars rise overhead, and the ground cools further. Somewhere, a scorpion waits, motionless, legs pressed to earth, tail poised. Around it, the unseen world moves, sending waves through soil and stone. To most creatures, the darkness conceals. To the scorpion, it reveals. Here, sight is optional, awareness is absolute.